Well, hello! It's Mr. Baruch. Did you miss me? Probably not, but I'm here anyway. So, you might be wondering, what exactly is it we're going to do? Well, I realize that we haven't had a chance to do a lot of student activities, so I figured, what if I just did it for you, and then you could watch along, follow the calculations, and it's almost like I'm your lab partner. Hey, you've had worse. So, what I'd like you to do is, if you haven't already done so, please download the student activity called a Decomposition of H2O2 that you'll find on your website. You'll find it under Student Activities, under AP Chemistry, and we're going to go through step by step the procedure. So the first thing I'm going to do is I'm going to read what the learning objectives are. So you can see there are 3 learning objectives. First is to identify the equivalence point in a titration based on the amounts of titrate/analyte if the titration reaction goes to completion. In other words, we're going to do something similar to MAVA equals MBVB, except without acid and base, we're going to titrate a redox reaction. Second, explain the changes in the amounts of reactants and products based on the bounce reaction equation for a chemical process. And third, represent a redox reaction equation using half reactions, which is kind of the most important part of this, showing you how to use half reactions to solve problems. We're going to use scientific practices 5A and 5F, which is using problem solving and then calculations. But ultimately our question is, how can we determine the percentage of H2O2 in a drugstore bottle of hydrogen peroxide? So what I have here is a bottle of H2O2 that I got from a drugstore. Now keep in mind a couple things. Number one, that bottle I just showed you has been sitting in a cabinet for probably over a year. And the fact that it's not a darkened bottle means that by now some of that peroxide, or I should be more accurate, some of the H2O2 within the peroxide has probably decomposed. So if you look at a normal bottle of peroxide, it should say somewhere around 3%. I doubt it's still 3%, but let's find out. These are the materials we're using, including the peroxide, a 10 milliliter graduated cylinder, 0.010 molar KMNO4, a well plate, 6 molar sulfuric acid, I'll explain why we need that, and a 1 milliliter pipette. So, here we go. Ready to be my lab partner? First, it says to measure out 1 milliliter of drugstore bottle hydrogen peroxide and dilute it with 9 milliliters of distilled water. So, putting on my safety glasses, I'm going to measure out, and I'm going to try to show you this. I'll be right here so you can see me doing it. Hold on, it's better that you see this than me. All right, go down here. So here's my bottle. I'm going to measure out the best that I can 1 milliliter of this peroxide. I realize you can't see what I'm doing at the moment because I can't point the camera and do this at the same time, but I will add the 1 milliliter, and then you can see, oh, or maybe not, turn around. Where is the opening? I know it's there somewhere. There it is. Well, you know, this is kind of hard to visualize. You're just going to have to trust me. That is 1 milliliter. I'm now going to dilute it with 9 milliliters of water. There's my distilled water bottle. Here, you can at least watch this part. Let me raise it up a little bit. So if I add 1 to 9, last time I checked, that should equal 10. And I know it's not the same as doing it yourself, but at least you get to watch me do it. And let me confirm it's exactly 10 to the best of my ability, reading the meniscus. 1 more drop. Okay, 10 milliliters. I'm now going to pour it into a beaker. Swirl it around a little bit, and I have diluted my peroxide. It's now 1/10. So let's go to the rest of the procedure here. Hope you're not getting dizzy. Pipette about 0.5 milliliters of your freshly made dilute solution of peroxide into a well plate. Here's my well plate. Let's see if I can get both these at the same time so you can see the well plate and the instructions. It's a little bit fuzzy. So, fortunately, the pipettes that I have they're actually graduated. They have lines on them to tell me 1 milliliter, 0.5 milliliters. So I can, to the best of my ability, try to get 0.5 milliliters. And what I'm going to do is I'm going to do it in 3 different well plates. So there is one. There's 2. And there is, let me do that again. I wasn't sure I got exactly 0.5. An air bubble in there. And there is 3. Okay, so I'm going to do this 3 times. So, what does it say to do as step 3? After I did that, add 2 drops of 6 molar sulfuric acid. So I'm going to do this to each one. Now, keep in mind, if this were an actual lab, only one person would do 1 at a time, and then the second and third, and even the fourth one could repeat it. So, 1, 2, 1, 2, 1, 2. All right. Now, all 3 are set. What am I going to titrate it with? Each person in your group should be titrating with 0.01 molar KMnO4 solution. This is it. It is a purple solution. KMnO4 has permanganate ion in it, and MnO4 minus is a purple color. You remember why it's purple? Yep, that's right. Manganese is a transition metal. All right, so let's see how many drops it takes. We'll try the first one. 1, 2, 3. You can see it's disappearing as soon as it hits. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I'm going to stir it around a little bit. I want to make sure it's actually disappearing. And it is. 16, almost missed. 17, 18. Let's see if that's enough. Nope. 19. 20. Ooh, it looks like it's staying. Hold on. Nope, not yet. 21. It's almost there. Come on, drop. 22. And now it stayed pink. So I'm going to write down that it took 22 drops. All right, let's try the second one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Let me mix around a little bit. 21, 22. Nope, still there. 23. And this time it took 23 drops. By the way, I'm recording it. Here, I'll show you down here in the data table. So I have 22 and 23. All right, let's try the last one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21, 22. Ooh, that might be it. And it is 22. All right. So, fairly reproducible, which I'm actually kind of impressed at because, using a pipette as a measuring device and using drops from a dropper, it's not always 100% accurate. So, let's go down to the calculations on the next page. So first, we're going to assume that every 1 drop of KMnO4 is approximately 0.05 milliliters. And that's a relatively safe assumption. It's somewhere in that vicinity. I have tested out before. So using the molarity of the KMnO4, which was 0.010 molar, let's calculate how many moles of KMnO4 I added. So first things first, let's do the average. So I have 22 plus 23 plus 22 divided by 3. On average, I added 22.33 drops. If I'm assuming it's approximately 0.05 milliliters per drop, then on average, every drop was about 1.117 milliliters. We're not going to worry too much about significant figures right now. We'll do it at the end. So, what does that mean as far as the moles of KMnO4 we added? Well, remember, molarity, hold on, make sure you can see this. Molarity equals moles over liters. The molarity of the solution was 0.010. The volume was 1.117, so if I divide that by 1,000, that would be liters. So that would be 0.001117. So I multiply that by 0.01, and that means my x is equal to 1.117 times 10 to the minus 5 moles of KMnO4. So in case I went too fast here, let me review. On average, it was about 22 1/3 drops to get this titration to complete. If we're assuming that every drop was about 0.05 milliliters, and that's reasonable, then on average I added about 1.117 milliliters for each titration. The molarity of the solution was 0.010. Molarity is moles per liter, so if I cross-multiply molarity times liters, and converting that to liters gets me that, I get x to be 1.117 times 10 to the minus 5 moles of KMnO4. So to be clear, that's how many moles of permanganate I added to the peroxide. Next, these are the half reactions that occurred. The peroxide broke into oxygen and H plus ions, giving off 2 electrons. The permanganate, using 8 moles of H plus and gaining 5 moles of electrons, turned into Mn plus 2 and 4 moles of water. Now these two reactions are balanced individually, but they're not balanced together because I have somehow lost 2 electrons and magically gained 5. That is impossible. But we know what to do because we've done this before. If I multiply everything here by 5 and everything here by 2, that will balance everything. So let's do that. And that will give me 5 H2O2 plus 2 MnO4 minus plus 16 H plus 10 electrons goes to 5 O2 plus 10 H plus 10 electrons plus 2 Mn plus 2, I am running out of room, plus 8 waters. Let's see if I can see the whole thing. Give me a second. So, I notice that I can cross out 10 electrons being gained and 10 electrons being lost, but if I look carefully, I can also see that I used 16 H pluses but created another 10 H pluses. I can get rid of 10 of those, leaving 6 H pluses behind. So now the balanced reaction is 5 peroxides, 2 permanganates, 6 H plus ions, makes 5 oxygens, 2 Mn plus 2, and 8 waters. So let me explain how this relates to what we just did. When we started, we added permanganate to peroxide. But we also had to add sulfuric acid to get the reaction going. Remember the 2 drops of H2SO4? That's because this reaction only works in acidic conditions. hence the 6 moles of H plus needed for every 2 moles of permanganate. You may have noticed when I added that there were bubbles being formed when I added the permanganate. That would be oxygen bubbles. You also notice that the second the permanganate hit, the purple color disappeared. That's because Mn plus 2 does not have a color, unlike MnO4 minus that does have a purple color. And in addition, we also created 8 moles of water. So, let's move on to the next part, which is what is the ratio of moles of moles of peroxide to moles of permanganate? Well, again, just from here, it is a 5:2 ratio. 5 moles of peroxide to 2 moles of permanganate. Moving down, using that ratio, calculate the moles of peroxide that were titrated. Okay? Well, if we go back to the top here, we know that we used exactly this many moles of KMnO4 on average. So if the ratio is 5:2, we can simply just do 5 H2O2 equals 2 MnO4 minus. That's the ratio. We know we used 1.117 times 10 to the minus 5 moles of KMnO4. So we can cross multiply and solve for x. So let me do that. And if my calculator is to be believed, x is equal to 2.79, I'll say round it to 2, times 10 to the minus 5 moles of H2O2. So I want to stop here for a second and make sure you're understanding what we did here. We are trying to figure out how much peroxide got titrated using the KMnO4. In other words, this is almost identical to when we did in acid-base titration, MAVA equals MBVB, moles of acid equals moles of base. Except this time it's moles of peroxide equals moles of permanganate. The problem that we have is it's not a 1-to-1 ratio, it's a 5:2 ratio. So we had to cross multiply. Another way to look at it is, what if someone were to say, hey, Mr. Baruch, couldn't I just use MAVA equals MBVB and replace A and B with like reduction and oxidation? Yeah, you could. But remember the rules of what to do when the numbers don't balance, when it's not 1-to-1? You could either do this method, or you could look back here and go, hey, wait a second, all I have to do is switch the coefficients and multiply the permanganate by 5 and the peroxide by 2, and that's exactly what we did here. We multiplied that by 5 equals x times 2, and that's how we got that number. So think about this for a moment. Make sure you understand it. You may want to go back and see if it makes sense to you. All right, bottom of the page. Now what I want to do is I want to calculate the molarity of the H2O2 that I titrated in that 0.5 milliliter sample that was in the well plate. So once again, molarity equals moles per liter. I am looking for the molarity. What were the moles of peroxide? Well, we just figured that out, 2.792 times 10 to the minus 5. It was a 0.5 milliliter sample, which in liters is 0.0005. So if I divide 2.792 times 10 to the minus 5 divided by 0.0005, I get 0.05584 molar. And again, yes, I know I'm using many more significant figures than I'm supposed to. I'm going to bring it back down when I'm done with the final calculation. So, the peroxide that I titrated was 0.05584 molar. So on the next page, now what I want to do is I want to calculate the moles of H2O2 that was in the original 10 milliliter sample that I made. Remember this beaker here? That's where I got all my 0.5 milliliter solutions from, right? So I would like to know in that beaker how many moles were there. Now that I know the molarity of the solution, I can once again say, all right, fine. Molarity is moles per liter. In that beaker, there was exactly 10 milliliters, which is the same as 0.010 liters. I can once again cross multiply and solve for x, which means there was 5.584 times 10 to the minus 4 moles of H2O2 in that beaker. Just so that you're not confused, these number of moles right here from the previous page, these were the moles that were in the well plate, in the 0.5 milliliter sample that I titrated. These were the moles that were in the beaker, which was a lot more because that was a 10 milliliter sample. It's the same stuff, just obviously there's more moles in 10 milliliters than there is in 0.5 milliliters. So, that is the moles of H2O2 that was in the original beaker. Next, calculate the mass of H2O2 from that calculation. Well, that's easy. We know how to convert moles to grams. I take 5.584 times 10 to the minus 4 moles, multiplied by the molar mass of peroxide, which is 2 hydrogens and 2 oxygens. That's approximately 34 grams. So multiply by 34, and I get 0.01899 grams of H2O2. With me so far? If not, pause it and do it yourself. So, if we assume that the density of the drugstore bottle of peroxide, remember the original bottle that we had? If we assume that the density of that is 1 gram per milliliter, and that's a fairly safe assumption because remember I said earlier that it's usually only 3% peroxide, which means it's 97% water, then let's calculate the mass percent of H2O2 in peroxide. And at this is the point where I want to make a distinction between saying H2O2 and peroxide. H2O2 is the exact chemical in H2O2 aqueous. So what I'm asking for is in the bottle that I bought from the drugstore that has H2O2 molecules in it, but also has water in it, what percentage by mass is just H2O2? How do you do percent? Well, part over total, right? So if I've already figured out from here that there was exactly 0.01899 grams, and 10 milliliter sample, again, assuming density of water is 1, that's 10 grams. If I do that and multiply by 100, so times 10, divide by 10 times 100, that means there was 0.1899% H2O2. That seems really low, because didn't we say it was originally a 3% solution? But hold on, remember what we did in the very beginning of the lab? We didn't take this bottle and titrate this bottle. We took 1 milliliter out of it and then added 9 milliliters of water, which means it's only 10% of the original bottle. So I have to multiply that mass by 10 because the original peroxide bottle, we didn't use that. We diluted it to 10%. So if I take 0.1899 and multiply it by 10, I get 1.899%. And basically I'm only allowed 2 significant figures, so it's about 1.9% peroxide. So yeah, it lost a lot. The original concentration was supposed to be 3%. That bottle's been in there for over a year. I'm not surprised it lost over a full % of its peroxide by now. But it does work. So, I hope you understand the student activity. I had a lot of fun showing it to you. I hope you enjoyed watching it. I realize it's not the same as being here. But hey, we got it done in less than half an hour. And I hope you learned something out of it. Again, please give me feedback if you have any questions or comments. I'd love to hear from you. Take care. See you soon. Bye.